The approach we have been using so far to solve these hypothesis testing questions is known as the critical value approach, or the CV approach. So let's just summarize that approach. We have three different scenarios. First scenario is a null hypothesis H0 has a mean that is equal to some value. I leave that space blank, but it could be 4. On the question we did, it was 4. The alternative hypothesis that goes with that would be H8, and it would be the exact opposite. Alternative hypothesis would be the mean does not equal that same value. So if it's 4 here, it would be 4 here. That would be the same value that would slot into there. That will lead to a two-tail test. A two-tail test means that there are two critical values, one here and one here. Zeros are going to be in the middle, and we need to work out the critical values so we can figure out what falls into our do not reject H0 region. Do not reject H0 and our reject H0. So reject H0 would be along here. And along here. Now, the critical values I showed you up until now were assuming that we knew the population standard deviation. So before I actually input the critical values, what I'd like to do is say that if we know the population standard deviation, so I'm going to put if population standard deviation sigma, I'll just put a check mark. If it's known, then we use a z distribution, and in that, under those circumstances, the critical value is going to be minus z of alpha over 2 and plus z of alpha over 2. On the other hand, if the population standard deviation sigma is not known, so I put an x by there, if it's not known, then we're actually going to use the, change the color, we're going to use the, let's use blue. Let's add another color, and let's make that color blue. So if the population standard deviation sigma is not known, then we have a t distribution, and our critical values are going to be minus t of alpha over 2, and with, remember, n minus 1 degrees of freedom. This is similar to what we did for confidence intervals, and plus t of alpha over 2 with n minus 1 degrees of freedom. And all that remains now is to get the standardized test statistic and see if it falls in the do not reject or the reject regions. And let me put the standardized test statistic up here. The standardized test statistic, I put STS, meaning the standardized test statistic. See, normally the test statistic would just be your sample mean. But your standardized test statistic has to standardize this value, so we have, from that we subtract the mean taken from our null hypothesis H0, and then we're going to divide that by the standard deviation of a sampling distribution known as a standard error. It's going to be sigma divided by the square root of n. And there you go. So when this is your scenario, equals versus not equals, you get a two-tailed test. And if you know the population standard deviation, then it's a z, use z critical values. And if you do not know the population standard deviation, use t critical values with n minus 1 degrees of freedom. So let's move on to the second scenario. So the second scenario, let's draw a line under this one. That's scenario number 1. And what I'm writing out now is probably would serve you well as a cheat sheet for your exams. But let's have a look. Scenario number 2. I'm going to get a null hypothesis. Let's see. We're going to get an H0 of the mean is greater than or equal to some value. It could be 4. And the alternative hypothesis is the exact opposite of that. So if we think that the student studies, say, for 4 hours a day, or at least 4 hours a day, then the exact opposite to that is student study for less than 4 hours a day. Whatever value is in here, the same value will be in here. And let's draw the region we're going to test. Now this will lead to a one-tailed test. As all these tests have 0 in the middle. And the I'll look at the arrow over here, it's pointing to the left, so the rejection region is going to be to the left. And so let's go in and select do not reject region. Again, just a reminder, we're always doing the tests on H0. Do not reject H0, the null hypothesis. Now on the other hand, on this side, to the left side, it's going to be the reject H0 region. And again, what we're going to say is that if the population standard deviation sigma is known, then we have a z distribution, and the critical value along here is going to be minus because it's to the left, and it's going to be z of alpha, not alpha over 2 because there's only one tail. So the probability that you make a type 1 error is all going to be on this side. We can't make a type 1 error on this side. We can only make it on the left hand side. So if we're prepared to take a 5% risk, say, of making a type 1 error, all 5% would be in this side, or all 5%, or alpha percent would be on that side. If on the other hand the population standard deviation is not known, then we're going to have a t distribution, and our critical value will be minus t of alpha over 2 with n minus 1 degrees of freedom. And again, the standardized test statistic in either case will have this formula x bar minus mu of h0 divided by sigma over the square root of n. And let's look at the third scenario. So the third scenario is going to be the null hypothesis is mu is less than or equal to. Now remember, we said that all the null hypotheses have an equal sign included in them. So that's less than equals, greater than equals, and the one above that is just equals. This one here is just equals. The alternative, or the exact opposite to that, HA, is that the mean is greater than. And what's that going to lead to? Again, this is going to lead to a test with only have one rejection region. They've all got 0 in the middle. You look from that the rejection region is going to be to the right hand side, so let's put the right hand side of center. So our critical value is going to go in here. Our rejection region is going to be to the right of our critical value. So I'm going to put reject H0 in here. Reject H0 and do not reject H0 is going to be to the left. So this is going to be do not reject H0, and then we're going to say, okay, if the population standard deviation sigma is known, then we have a z distribution, and our critical value is going to be plus z of alpha. Otherwise, when the population standard deviation sigma is not known, then we're going to have a t distribution. And our critical value will then be t plus t of alpha with n minus 1 degrees of freedom. So there are 3 scenarios that we have. Let's scroll down, let's make that a little bit smaller so we can get them all on one screen, if we can do that. Okay, so there are 3 scenarios for the critical value approach. First one is a 2-tailed test, there's 2 rejection regions. The second one here is a 1-tailed test with rejection to the left, and the third one is also a 1-tailed test with rejection to the right. There are only 3 different scenarios. Any question you get can be fit into one of these 3 scenarios. Do not try to force any question into a scenario that doesn't exist there. These are predetermined scenarios where the whole theory flows from these 3 scenarios. It is possible for the theory could have been set up a different way, but it wasn't. This is the way it was set up. And what I often tell you in class is that this is the convention. It's the convention that in this country, in the USA, we drive on the right-hand side of the road. It doesn't mean that it had to be that way. A convention could, in other countries, has been set up, you drive on the left-hand side of the road. If you go to England or Cyprus or Japan, these countries and certain countries in Africa, they'll drive on the left side of the road. So the fact that we're used to driving on the right-hand side of the road is just the convention. Another convention is that clocks go clockwise, which the time increases to the right-hand side. I have actually a clock, which when we're in class, I bring to class to show students, actually works backwards. If somebody just decided that clock should go, time should increase to the right on a clock or a watch, it doesn't have to. That was the convention. That's what somebody decided, and that's what we go along with. In the same way, these 3 scenarios are the convention. They could have been set up differently, but they weren't. The whole theory, though, stems from these 3 scenarios. These 3 scenarios, scenario 1, 2, and 3. So sometimes on a question, they don't actually give you the null hypothesis. Sometimes they give you the alternative hypothesis. And if they do, you still proceed the same way. Even if a question gives you the alternative hypothesis, so they say, oh, we want to check that students do not study for 4 hours a day, and they actually give you the alternative hypothesis, you will still run the test the same way. It may seem a bit odd, but if you think it through, that's the right thing to do. If, for example, they asked me to check that students do not study for 4 hours a day, I would run this test, and I would still check to see if H0 is correct or not. But that doesn't matter. Once I find out if the null hypothesis is, say, for example, correct, it means that the alternative is not correct. So I always get a result to both. Even though I test H0, I get automatically a result to HA. If I find out that the null hypothesis will be rejected, it means that I'm going to agree with what's in the alternative hypothesis. So we're going to do some examples. There are several examples for you to do. I'll do some as well to show you that, but bear that in mind.